Alright, so today we're going to tackle this concept of continuity and then also try to speed through the intermediate value theorem. So going to be bum rushing the end of this first notes packet. Hopefully it's not too bad for us. But anyways, we know continuous means, in layman's terms, right, if you had to put a definition on it before you get to calculus, continuous basically is when you can draw a function without picking up your pencil or without picking up your pen, right? When you graph it, there's no weird issues like asymptotes or jumps or breaks or any types of gaps. It's basically one smooth, connected graph, right? You could graph it without picking up your writing utensil. But we know as far as a mathematical definition, that's not precise enough. But you can't really define continuity until you know limits, and you can't do limits until calculus. So we haven't really gotten any good concrete definition for continuity until now, right? You know what it means, we know what it looks like, but what's the actual formal definition? Well, it's going to involve three parts, and you have to have limits before you could get to it. So that's why you've never really had it defined for you before. Anyways, let's go for it. A function f is said to be continuous at x equals c if and only if, and three things have to be true. The first thing is f of c exists, right? You cannot be continuous at a point if there is no point. This tells me that there is a solid dot somewhere, right? And that makes sense. Yeah, the function cannot possibly be continuous if there is no point. Duh. Alright, second thing, a little bit harder. We're going to need the limit as x approaches c to also exist. Now remember, this is a pretty heavy statement. That statement means the limit from the left exists, the limit from the right exists, and moreover, those two one-sided limits equal the same thing. Right? So this kind of carries a lot of weight. The limit overall exists also means the limit from the left exists, the limit from the right exists, and both of those two things match. They give you the same value. But here I have the point exists, which means there's a solid dot somewhere, and here I have the limit exists, which means you're approaching, you're converging to that same location from both sides. And remember, I kind of talked about limits as being the behavior of a function, where the graph is supposed to be. So here is where the graph is. Here is where the graph is supposed to be. And then the third thing, we're going to tie them together. The limit as you approach c has to equal the function value at c. Remember, f of c means there is a solid dot somewhere. That is where the function exists at that specific x value. The limit tells me where is it supposed to be, what's the behavior as I approach from the left and also from the right, and those two things better be the same. And then that third thing kind of ties them together. It says the function exists where it is supposed to exist, right? That limit value has to equal the function value. So let's draw some examples dealing with some situations. First one, we're going to sketch a function so that the function is not defined. Now these are going to be variable in how you answer them, right? There's infinitely many things you could draw for all of these answers. I'm just going to draw one sample for each that satisfies the given criteria. So here we go, part A. Draw a function so that f of c is not defined. Well, I could do something like this. Right, just skipping that point at x equals c. That's fine. Again, you could do lots of other things. They would probably all be equally as right. But just make sure there's no solid dot anywhere where the x value is c. Okay, part B says the limit does not exist. We saw a bunch of those when we did limits graphing. Right? You could draw something like a step function where the limit from the left is one value and then the limit from the right is a different value. You could do an asymptote where one side goes up, the other goes down. Lots of different things you could do, but here we just want the limit to not exist. So the limit from the left and the limit from the right better not be the same. Okay, part C is probably the hardest. It says the function is defined, so there's a solid dot somewhere, and the limit exists. That means you're approaching and converging to the same spot from both sides. But it's not continuous because the limit doesn't equal the function value. So here I'm going to kind of draw something similar to what I had on part A. Right? So there I know the limit exists, but the function doesn't. And then here I'm just going to put that solid dot somewhere else. right? That's definitely not continuous because there's no way you could graph that all at once without picking up a pencil. But here, let's check it. The function is defined, yes, because I've got the solid dot. The limit exists because you're approaching the same thing from the left and as you are from the right. But I see that those two values aren't the same. Remember, the limit tells you where that function ideally should be, where it's supposed to exist. The solid dot is where it actually is. And if there's any type of a disconnect, if those aren't the same thing, then the graph is going to be discontinuous. And then part D is easiest, continuous. You can literally just draw any function as long as you don't pick up your pencil, right? Continuous means the point exists, right? There's definitely a solid dot somewhere, and then you're approaching that spot from both the right and the left. So continuous, easiest thing to draw. Okay, next let's talk about the different categories of discontinuities. There's really going to be 3 types, but 2 categories. We have point discontinuities, jump discontinuities, and then asymptotic discontinuities. These 2 are going to be considered removable. Oh, sorry, no, just the point. Just this first one is removable, and then these 2 are what we consider non-removable. And I'm mostly on the screen. Okay, let's fix it. So we have the point, that one's removable, but then the jump and the asymptotic, those are both non-removable. Point discontinuity is pretty self-explanatory. It just means there's literally one point that's messed up. The point could be undefined, so it could be something like this example A, or the point could be somewhere misplaced like it is on example C up above. Either way is fine, but a point discontinuity is literally when it's discontinuous just because of one point that is gone, one point that is missing, or one point that has been removed. If you could fix the issue, if you could fix the discontinuity by fixing one specific point, then that is what we categorize as removable. Right? One thing, if I could just fill that dot in, it would now be perfectly connected and continuous. So that's why we consider it removable. Jumps and asymptotic discontinuities, you're going to have much bigger issues. You can't solve both of those by just moving or filling in or fixing one spot. So they're non-removable. Jump discontinuities are basically any type of a piecewise function whenever you have a jump or a gap in between your respective y values. So that's usually when the limit from the left and the limit from the right are 2 different values. And then, spoiler alert, the asymptotic discontinuities, well, that's going to come up when you have an asymptote. So something like that would be a perfectly good asymptotic discontinuity. So point, really easy. It's just off by 1 point. The jump, also pretty easy. You can visually see there's a jump between the y values. Asymptote, pretty self-explanatory. So the 3 types, I think, are pretty easy to identify. And then the categories, the holes, the point discontinuities, those are the only ones that are removable. All the other ones, the jumps and the asymptotes, those are non-removable. Non-removable means you cannot fix it with 1 point. Okay, let us go through and let's do these examples on the back, which is mostly just pre-cal. We're going to go through it pretty quick. We're going to sketch, I guess we'll sketch the graph last. We're going to identify the x values where there's an issue, where there's a discontinuity. Then we're going to classify it as a point, jump, or asymptotic. Then we'll also categorize it as removable or non-removable. And then we'll sketch. I think I'll probably actually sketch the graph first because I think that's the easiest way to get this answer. All right, first one, of course, you'd want to factor first. Plus 2 minus 2, this graph is going to reduce, and it's going to end up looking really similar to the line x plus 2, but we know because this factor that reduces, you're going to end up having a hole at x equals 2. So the graph is going to look really similar. It's about the same as the linear function x plus 2. Except this rational isn't equal to the line. This rational matches for 99.99999% of the points, but there's just the one that's been removed. Okay, so here we go. Obviously, x equals 2 is the spot where we have a discontinuity. It is just a point discontinuity, and that means it is removable. It's pretty easy. Just testing some vocabulary and some terminology. Next one, we've got a typical reciprocal function. It looks like it's shifted 3 to the right. It's going to be up here on the right, and then if you plugged in 0, you would get a negative 1/3. So the y-intercept It's negative. So the graph is going to look more or less like that. Remember, sketch, right? It doesn't have to be super accurate. Sketch. Okay, so let's see. X equals 3 is the issue. It is asymptotic, which is non-removable. I'm getting lazy. I don't want to write out non-removable, so I'm just going to put NR, non-removable, for this page. Example C, we have a step function. It's shifted, also 3 to the right. You have the upper step at 1, the lower step down at -1. So obviously x equals 3. Now, you could argue that there's a point discontinuity as well, right? Because there's no solid dot anywhere. But the bigger issue for sure is the jump discontinuity, right? Because there's this gap in between the limit from the left value and the limit from the right value. We would really care more about categorizing that as a jump, which is non-removable. Only the points are removable. Okay, part D, we have a piecewise function. So I'm thinking to myself, it's probably going to be a jump. Let's go ahead and graph it and confirm. We're going to graph the linear function x plus 2 for everything less than 1. So if you plug it in, 1 plus 2 would be 3. And then let's see if we graph the other one. I think that one would have an intercept. Let's see if you wanted that to be 0. I think it's going to cross the x-axis at 2. So let's see. Plug in 1, 2 minus 1. So that point's going to be right here. And then if I plugged in x equals 2, 2 minus 2 is 0. So that one's going to look like this. If you want to rewrite it as negative x plus 2, you can see the slope is -1, but the intercept is 2. So right, if I would have extended that line backwards, they would have intersected, but we didn't want to. This x equals 1 is the transition point where you switch from one to the next. But okay, we should be able to graph linear functions. So here at x equals 1, that's where I am discontinuous, that's weird, discontinuous, and it's clearly going to be a jump discontinuity, which is, how about non-removable? There we go, I eventually got it, non-removable. Part E, sorry, getting ahead of myself. Part E, let's see, that's a parabola shifted up 1 unit. That one is not going to have any discontinuity, right? So no points of discontinuity. It's continuous, right? Another thing you could say, it's continuous for all real numbers. Right, we know those parabolas don't have any holes, we know they don't have any jumps, we know they don't have any asymptotes. They're a really nice graph, right? All polynomials are going to be continuous for all real numbers. Rationals, a little bit more troublesome because of the asymptotes. Piecewise functions usually have the jumps, and then rational functions. If you have the factor that reduces, you can have the whole also. Okay, the last one, speaking of rationals, let's try to factor it. We have the x that would factor out, and then we have the x minus 3, then you have the x that reduces. So this one's going to end up looking really similar to what we graphed up ahead on part B, right, up above. So this part F is going to look really similar to the one we've already done. It's going to have the asymptote at 3, and then the graph's going to exist up there, and then the graph is going to exist down here. Right, so we know definitely at 3, there's the asymptotic discontinuity, which is non-removable. But then remember, I also had this factor that reduced. And when you have that factor that reduces, you're going to have a hole at that specific value. So here this graph is going to have one extra thing that's different. Instead of having a y-intercept, remember at that spot where the x value is 0, we have that y-intercept is actually missing. So at x equals 0, we have a point discontinuity, which is removable. So that one had the asymptotic, which is the bigger issue, which is non-removable, and then we have the point. Remember, that point comes from the hole, which comes from that factor that had reduced. Okay, so wonderful. Let's kind of be done with the terminology now. Let's flip it over, and let's look at the next paper. Okay, let's actually do some types of questions we may see on the AP exam. Right? Let's actually put this into some legitimate practice. Use the definition of continuity to prove that the function is discontinuous at 2 if a equals -4, and then we're going to go ahead and sketch the graph to check the answer. Okay, I don't know how much we're going to sketch the graph. You could always just type it into the calculator at the end to confirm, but I don't know. We'll see. Let us go for it. Here it gives me the a value, right? The question tries to trick you by having this a value in the function at first, but then it straight up tells you what that a value is. So let us go ahead and just kind of plug that in. It says the a value was -4. So I have -4x plus 7. Should be able to graph that. Should also be able to graph 1. Right, so this function is going to look mostly like the linear function, -4x plus 7. We're going to graph that line for everything except 2, and then at 2 it tells us the point is going to be up at 1. So let's go ahead and graph this sucker. 1, 2, 3, 4, sure, and then let's test it. It's going to go up to 7. I don't know. 1, 2, 3, 4, 5, 6, 7. Okay, close enough. And then let's just start plugging in some x values. Like I got 0, 7 would be a point. See, if I plugged in 1, it would be up at 3. If I plugged in 2, I think that point would be down at -1. And then if you plugged in 4, sorry, I guess, yeah, 1, 2, I definitely moved that over way too far. And then if I plugged in 3, looks like the point would be at -5. So on and so forth. So it should go down 4 over 1, down 4 over 1, down 4 over 1, so on and so forth. That's what it means to have a slope of -4. Your graph doesn't have to be super precise or super accurate. Mine usually will not be. But as long as you get the general shape right, you're going to be okay. So there's the line, which I've got graphed for everything except 2. And then it says at 2, the point is actually going to be up at a +1. It's supposed to be down at -1. But it actually exists up at the +1. Okay, so let us check. Use the definition of continuity. So we have to ask ourselves 3 things. Does the point exist? Is there a solid dot somewhere? Does the limit exist? Am I approaching the same location from the left as I am from the right? And then the third thing is, does the point equal the limit, right? Do those 2 things mesh? Let's check. Does f of 2, right, 2 is the only thing where it may potentially be an issue. I know that's going to be continuous everywhere else. I know that point is fine, right? So we're really just checking this transition point. We're checking at what happens when x equals 2, right? So x equals 2 is what we're investigating. Let's see. Does f of 2 exist? Well, yes, it like literally tells you when x is 2, the function value is 1. Yes, so that one exists. I guess we should add the s. Yes, the function exists, so it's not the first criterion that fails. There is a solid dot somewhere, and that solid dot is up at 1. F of 2 equals 1. Okay, next thing. The limit of the function as x approaches 2. Does that exist? Right, let's check it. Well, I have the limit from the left. Hop on this function, come back towards it. That limit from the left is taking you towards this spot, which is at a height of -1. The limit from the right, hop on the right side, come back towards your target, also converging towards this same location. So those match, which is really good. The limit as x approaches 2 is -1. So certainly that limit exists, right? You are approaching the same thing from both the right and the left. So that overall limit does exist. But then here's the third thing. Does your limit value as I approach 2, does that equal the function value at 2? Let's see, the limit is -1. That's the value where the function is supposed to be. The solid dot actually was up at 1. Ooh, so look at that. Those 2 do not match, right? Those things are not the same. The function exists. There is a solid dot somewhere, but that solid dot is not where it is supposed to be. The limit tells us where it's supposed to be, the function value tells us where it actually is, and then we need those things to match. Right? So here we could say, therefore, not continuous, I'm just going to abbreviate it, when x equals 2. Definitely not continuous because the limit doesn't equal the function value at that specific point. Okay, next one. Used, I guess we did get the graph done too. That was really nice. All right, next one. Use the definition of continuity to find k. K is some constant. We're going to figure out what it is. Use the definition of continuity to find k so that the function will be continuous at x equals 2. Okay, so we're going to want the function to be defined. We're also going to want the limit to exist, and then we're going to want those 2 things to be equal. How you're going to end up doing this is really pretty simple, right? I have some line, x plus 3. That's pretty easy. Let's graph it. 1, 2, 3. There's the y-intercept, and then we have the slope of 1. So at 2, it's going to be up at 5. So we've got that part already graphed. Wonderful, right? It's pretty easy. And then it says, okay, this other line, I don't know what the slope is yet. That's what the k value represents, right? The coefficient of the x is the slope. I want to know, what is the slope of the line going to be? If the y-intercept is 6, so let's see, up here is 6. If I want to go through this point, but I also want this graph to be continuous. Obviously, I'm not going to end up graphing this line between the 0 and the 2. At 2, you're going to pick up with this transition point, and then you're going to continue with the second line. But I somehow need to figure out, if this is my y-intercept, which it has to be, what is the slope then, so that this line, starting at this point, is going to also connect through this point and then continue on its merry way, right? So we're basically figuring out what's the slope that's going to connect this point to this point, which, yes, you can just kind of count the rise and the run if you want, and you should be able to get, let's see, it goes down 1 over 2, so we're kind of thinking that that slope is going to have to be a negative 1/2, right? So if you can see the graph, you should be able to count, okay, what's the slope of that line going to have to be? And then it would continue on in that same slope. But there's a pretty easy way to prove it mathematically. If you want two graphs to intersect, which we do, we have the first graph, and we're trying to figure out when is this second graph also going to connect, and when is it going to intersect. Well, if I want to figure out when two things intersect, what you do with the two equations is you just set them equal to each other. Right, so we're going to need those two graphs to intersect, so I'm just setting the two equations equal to each other. Now, I don't always need this line and this line to intersect, right? I only need them to intersect at this one specific point. So now I'm going to plug in at x equals 2. So 2 plus 3 equals k times 2 plus 6. You don't need the whole entire equations to intersect. That's not really possible for lines. You only need them to intersect at your one specific point. And then you can just solve for it. 2 plus 3 is 5. This is 2k plus 6. Subtract the 6 over. And then here I end up getting the negative 1/2. Okay, so let's go ahead and check it. If I plug that value in, you'd still have the x plus 3 for all the values less than or equal to 2, and then I would have your negative 1/2 x plus 6 for everything bigger than 2. Right, so here is my y-intercept. If I went down 1 over 2, yep, down 1 over 2, down 1 over 2, yep, we kind of confirmed what we had suspected earlier, that that slope of the line should end up being a negative 1/2. It's not too bad. If you want things to be continuous, you're going to need them to intersect, so I just set the two things equal to each other, and then you have to just plug in the x value where you need them to intersect. The next one's a little bit harder, but it's the same idea. It's just going to have a little bit more algebra going on. So let's finish up this last one with continuity, and then we will get into the intermediate value theorem. All right, so use the definition of continuity to find a and b so that the function f will be continuous everywhere given, and it gives us the rest of this function, right? We could try to graph it if we want. The question doesn't really ask us to, but we could. Let's see, we got negative 17. So everywhere from negative 3, let's see, that's a solid dot 2. So there's the first part of the function, and then it's going to be up at 3 at 1. So here's 1. It's going to be up at 3. Cool, and that's going to be an empty dot. So I've got the first piece and the last piece already done. Those are just two horizontal lines. And it's basically trying to figure out what's the slope and then what's the y-intercept for this middle line that's going to magically connect the two pieces. Again, if you've graphically got it done, you can kind of just count the total rise and the total run, and then you can just break that down and then figure out what the corresponding individual slope and step size needs to be. From there, you can kind of figure out where your intercept is, but doing it algebraically isn't too terrible either. But we're trying to figure out what's this magical line going to be. If you have the correct slope, but the y-intercept is wrong, well, it's not going to connect. And if you've got the right intercept, but your slope is wrong, then it's not going to connect. You're going to need both things, right? The A value is the slope, the B value is that intercept. We're going to need both of them to magically fall in line so we get that one piece that's going to connect them, right? There's lots of ways you could do it, but here I'm going to show you probably the easiest, most straightforward way. All right, well, going back to what we said earlier, I'm going to need these two to intersect. So I'm going to set the first function equal to the second function. And then I'm going to plug in my x value. Now I'm going to need those two to intersect at that first transition point. So I'm going to plug in at -3. So there I have one equation, right? Very good. Now the second thing is I'm also going to need those two to intersect. So ax plus b is going to have to be equal to 3, and then those two are going to intersect when x equals 1. That's the second transition point. So I'm going to plug in 1 for the x value. So here I have a systems of equations. I've got that equation with a's and b's, and I've got that equation with a's and b's. And we're going to solve that either with elimination or with substitution. Doesn't really matter, whatever you prefer. You should know how to do this going back to Algebra 2 or even pre-calc, but a 2x2 system should be pretty easy to solve. I'm going to go ahead and just use elimination. I'm going to copy this one. Now, if I copied this one right here, a plus b equals 3, well, nothing would eliminate. I'm going to take this and I'm going to multiply it by -1. Because when I take that second one, right, there was your equation number 1, here was your equation number 2. If I take that equation number 2, and if I multiply it by a -1 scale factor, now when I add the two together, the b's will eliminate. I have -4a equals -20, which will end up enabling you to solve for the a value. And then once you have the a value, go back and plug it into one of your equations, and you can also get the corresponding b value. So let's go back, plug it in here. So I know b is going to be -2. Okay, so let's think about this, right? It tells me the slope of that line, if I'm thinking about this middle piece, the slope should be 5. So I've got 5x and then -2. So if I graphed this line, 5x minus 2, it had better somehow connect from this point up to this point. And it would, right? If you actually count up 5 over 1, or if you went down 5 over 1, down 5 over 1, it would actually be the perfect line that's going to connect the two, and then you would have the solid dot, right? Since this one's inclusive, the solid dot will always override, and it will fill the empty dot. So even though that one was empty, so that's why it started as a hollow point, whenever we graph that middle function, it's got the or equal to bar, and then the solid dot always takes precedence, so it would graph over, and it would fill in the empty dot. Right, so whenever you're answering these questions about continuity, just remember, you need the functions to intersect. So you just take the two equations and then you set them equal to each other. But you don't need the entire equations equal to each other. You only need them to intersect at one specific point. So I take those functions equal to each other, plug in the value that the transition point is. Here it was a little bit harder because I had two transition points. So I set those two equal, plugged in that first transition point. Then I set those two equal, plugged in the second transition point. And I had some extra algebra to do with that systems of equations. But hopefully the algebra isn't the reason why you're missing a calculus question, right? Yeah, that's pretty much it. Continuity, not designed to be terribly difficult, can be a little bit algebra heavy, but that should be in your wheelhouse at this point. Okay, let us try to go ahead and finish this packet while we're at it, right? Let's do the intermediate value theorem, which is altogether way too wordy to say. So from now on, I'm probably just going to refer to it as IVT, right? Intermediate value theorem, IVT. Let's go ahead and read this definition. Let's get confused. We'll draw some pictures, and hopefully the pictures will help make sense of it. Well, I guess before we get to the definition, let's read that statement up at the top. Since a person's height is a continuous function of time, if a child has a height of 58 inches at age 11 and a height of 64 inches at age 14, then the child's height took on every value between 58 and 64 at some time between the ages of 11 and 14. Like, we know growing doesn't just happen instantaneously. They don't just like wake up 5 inches taller. If you do, I mean, at least at some point in the middle of the night, you were every single one of those heights at some point, right? You don't just magically instantaneously grow. It's a continuous, gradual process. So if you start at one value, 58, and you end up at another value, 64, I know at some point between that initial time and that final time, at some point in between, this kiddo was 59 inches tall. They were also 62 inches tall. They were also 63.99999 inches tall, right? Every single value between these two, the initial and the final, has to be hit. And it's going to be hit at some time between the initial time and the final time. Like, we know intuitively that makes sense. Let's try to take that same concept and now apply it to a function with a graph, because that's what the intermediate value theorem is all about. Remember, intermediate means in the middle. Inter is a prefix. It means between. Intermediate, in the middle, value theorem. All right, let's go for it. You have some conditions. One, the function has to be continuous on the closed interval. So, yeah, we're going to want no holes, no jumps, no asymptotes. Got to be continuous. Also, we're going to want the endpoints to be different heights. I do not want the left height and I do not want the right height to be the same. I want them to be different. It doesn't matter which one's bigger or which one's smaller, but I want them to be different. And then I need my k, which is the desired value we want to hit. I want that output to be in between my initial and my final. And then it says, if all those three things are met, then there exists some number c, this is an x value, that k value was a y value, there exists some number c between a and b in my interval for which, or so that, f of c equals k. Alright, seems strange, let us draw a picture. I'm going to go ahead and just draw something that's pretty easy. Let's call this a, we'll call this point b, we'll call this f of a, and we'll call this f of b. Right, so let's make sure I've got all my conditions done. Is that graph continuous? Certainly, right? I drew it without picking up my pencil. It's continuous. Are the endpoints different? Does f of a equal f of b? No, one of them is down here, the other one's up here. Here I put the initial as the lower, and then the final value is higher. You could have easily have drawn a graph that went like this. Doesn't make any difference. You just need the endpoints to be at different heights. That's what this middle statement says. And now here, let's pick a k value. I need a k value between f of a and f of b. So somewhere in the middle, like let's say here. It doesn't have to be exactly in the middle. But it says somewhere in this interval, so somewhere between a to b, there is going to be a value that gives you out k. Kind of think about it as going backwards. Here's my k value, right? It's in between. Is there a point on the function that hits it? Well, it looks like yes, there would be a point on that function, right? This point certainly is going to have a y value that is going to equal to k, and then that point's corresponding x value is between a and b. So that would be the answer. That's the x value in my interval that produces out your desired k. Now, you could pick any other value. Like here, let's try this one. How about we'll call that one k2. There's going to also be a point on the graph that hits that y value, and then that point is also going to be an x value in my interval. Any y value in your interval, right? You could pick something up here close to the endpoint, or down here close to the endpoint, but any y value in between your starting and your ending values, any y value is going to get hit, and it's going to get hit at least once. K3. Right, that's what your intermediate value theorem says. If your function starts and ends at different spots, and it's continuous, right? The only way that this function can get from your bottom point up to your top point, since it's continuous, it's going to have to pass every single point in the middle at least once. Now, it could happen multiple times. Like, let's say you had a function like this. Your graph could go up, could go down. It could do all sorts of things, right? And maybe this is your k value. And maybe you hit that k value 1, 2, 3, 4, 5 times. It doesn't matter. What this theorem says is that if your function starts and ends at different heights and it's continuous, it's going to hit it at least once. Now, you got to be careful about overextending this theorem. It doesn't tell you, Like, hey, the function can go above or the function can go below. That's possible, but you don't know for sure. It doesn't tell you that it's going to hit multiple times in the middle. It's possible, but you don't know for sure. All you know 100% of the time, every single time, is that if your function starts and ends at different y values, all of these y values in the middle get hit at least once. The function could go higher than the upper value, or the function could dip lower than the lower value. You don't know that, but it's possible. All you know for sure is that all of these points in the middle get hit at least once. Could be multiple times, but it's going to be at least once. Right? Hopefully that makes sense. It can be a little bit weird, but just remember, intermediate, in the middle value theorem. If your function starts and ends at two different points, every single one of those y values in the middle gets hit at least once. Could get hit multiple times, and the function could go up above the higher point, or the function could go down below the lower point. That's not 100% guaranteed. All you know for sure is that all the stuff in the middle gets hit, and it gets hit at least once. But again, you need the function to be continuous, and you need the start and the end points to be at different heights. All right, last two examples, then we're done. We're done with this whole notes packet. It's a monumental moment. Use the IVT to show that f of x equals x cubed minus 3x. Show that that takes on the value 1 for some interval between negative 2 and 4. Okay, let's check it. Is this function continuous? Certainly. This function, you can just tell, you don't even have to do any work. Just write f of x is continuous. Sure. Right, that function's a polynomial. We know it's going to look something more or less like this since it's cubic, but we know polynomials are always continuous. If you want to cite because it's a polynomial, that's fine, but you don't really need to. Now the second condition, we need to check, do the endpoints give you out different heights? So let's try. F of negative 2, and then f of 4. Let's plug in the left side, plug in the right side, and we are going to want them to be different values. Negative 2 cubed minus 3, negative 2. So let's see, that's negative 8, and then that's going to be plus 6. So negative 2. So if you plug in negative 2, it looks like you get out negative 2. If I plug in 4, 3 times 4. So that would be 64 minus 12, 52. Okay, so this graph grows pretty steeply, right? It's cubic. We know on the left side, it's down at a height. Let's kind of just try to at least sketch a little bit of a graph. Over here at 1, 2, 3, 4. It's just barely negative over here, right? It starts at this height of negative 2, and then it ends pretty tall up here at a height of 54, right? That diagram may not be to scale, who cares? But I know the graph starts down here at negative 2, it ends up here at 52. That's what we just checked. I know it's continuous, so any of these values in the middle, right, are gonna get hit. There's no way the graph can get from down here to up here unless you cross the middle, and you're gonna have to cross it at least once. We know that because it's continuous. The function could drop down and then come back up, or maybe it goes really high and then comes back down. You don't know that. All you know for sure is that all of this stuff in the middle between these values is going to get hit at least once. So let's check. Is 1 in between your two values? Is it between my starting value and my ending value? Certainly, right? 1 is going to exist. So there's going to be at least 1 point on the function so that f of something is going to equal 1. So we could say, like, yes, there is a point C, and that C value is going to be in your interval. It's going to be, I guess we know the interval, it's not A and B anymore. It's going to be between negative 2 and 4. There is some point here between negative 2 and 4. There's some x value that's going to produce out a value of 1. For some C value in my interval. So yes, certainly, we know this theorem guarantees us that the function is going to produce out 1 at some point in my interval between negative 2 and 4. Sorry, that got a little sloppy. Oh well. The answer key online, the picture probably looks a little bit nicer. Alright, one last one, then we're done, which is good, because I'm very quickly running out of steam. Determine if the IVT holds for the given value of k. If the theorem holds, find the number c so that f of c equals k. So find the x value. If the theorem does not hold, give a reason. Draw a sketch of the curve and the line y equals k. Okay, here's just a little pro tip. We're going to have multiple theorems this year. IVT and squeeze theorem, those are the first two. If you ever get a question that says, determine whether or not the theorem holds, it's going to hold, right? I'm not going to give you a question where the theorem doesn't work. Now, the AP exam may, I really doubt it. They're not going to give you a question where the theorem doesn't work because then it's too easy of a question, right? So just kind of be smart, be anticipating how these questions are going to unfold. If you're in the situation where you're trying to debate, hey, is this theorem going to work or is it not? It's going to work, right? It's going to work. Otherwise, the question would be too short. It'd be too easy. So basically, we're going to prove that the IVT works, which, yeah, it's going to. Then we're going to find the x value that gives you out that specific y value, and then we'll draw the sketch. All right, but first thing, is the function continuous for my interval 2.5 to 7? Now, here's your function. I know that function is not always continuous. I could graph that function, and it's going to have a vertical asymptote at 2. That's 2, 3, 4, 5, 6, 7. Okay, good enough. So that graph does have an asymptote there. Let's see, the y-intercept would be like -1/2. So this graph is going to look something more or less like this. It does have a discontinuity, but that discontinuity is not in my interval. My issue is at x equals 2, but I'm really only caring about 2.5 and then to the right. So yes, the function is certainly going to be continuous for my interval. The issue is not in my interval. The issue is over there to the left, right? So yes, it's going to be continuous. That's great. Let's check the endpoints. Let's plug in 2.5, and let's plug in 7, and then let's get these two corresponding output values. Let's see, if I plug in 2.5, so I have 1 over 2.5 minus 2, so it's going to be 1 over 0.5, 1 over 1/2, which is 2. So at this specific point, this graph is definitely not to scale. That's okay. This point is going to be up at 2. Not to scale, whatever. At this specific point at 2.5, the y value is 2. How lovely. Let's test the next one. 1 over 7 minus 2. That's pretty easy. 1/5. So at this point, the graph is at a y value of 1/5. So that's good. Those two things were different, but that's fine. We wanted them to be different. The starting point and the ending point need to be different y values. If they were the same, this theorem wouldn't make sense, right? Because this is the middle. You wouldn't have a middle if the two values were the same, right? So you need the starting point and the ending points to give you different y values so that there is this range in between them. And then this theorem says, hey, all of these y values in this graph are going to get hit at least once. That's what the intermediate value theorem guarantees us. Last thing we got to check. Here's your k value. Is 1/4 between your starting and your ending? I guess you're starting up at 2 and your ending is 5, but 5 is the smaller one. Is 1/4 in between those two original points, right? Here was the ending value, which was lower. Here was the initial value, which was bigger. Is the k value that I'm investigating, is it between those two? Well, convert these to decimals if you need to. Oops, just kidding. I got that backwards. This would be 0.20. That's 0.25. That's just 2, right? So now we can see if you convert it to the decimals, yes, that's pretty good. So we would say, therefore, yes, IVT holds. The theorem is going to work. There is going to be some number that gives you out 1/4. And that number is going to be between 2.5 and 7, right? There's going to be some x value in my interval that produces out a 1/4 value. Okay, now this is pretty easy. Don't overthink it. We have the function. Here, I'll write f of c again. We have this function. We don't know the x value, but I do know what I want the y value to be. So here I'm just going to take this function, and I'm going to set it equal to 1/4. If you have a function and you know what you want it to be, You just set the function equal to that number, and then you can solve it for x, or you can solve it for c. I don't care. You can work it with x's, or you can plug in the c's. It doesn't make any difference. But you're just going to go back, set your function equal to this number, and then solve. And then that's how you answer the part B. So let's go for it. The ones are the same, so that means c minus 2 is going to have to be 4. So that means the c value, I think, is 6. Okay, so yes, you set the function equal to your desired output, solve for it, and it looks like right here at 6, that would be the point where the y value is 1/4. And just to double check, is 6 in between your interval? Is it between your original x value and your final x value? Yes, of course it was going to be. So that's your IVT. Everything in the middle gets hit. If your function starts and ends at 2 different heights and it's continuous, every single y value in the middle is going to get hit at least once. That's all the theorem says. The stuff in the middle could get hit multiple times. You don't know that though, but it could happen. The function could rise up above the bigger point, or the function could drop down below the lower point. That's possible, but you don't know for sure. All that's guaranteed is that all the stuff in the middle gets hit at least once.